Hello, thank you for watching this video. So in this video we're doing question 11 of November 2021 question paper mathematics paper 2. And the topic is Euclidean geometry, as you can see over here. And we'll be doing or proving the Tan-Chord theorem of 11.1, and then we move to 11.2. What are they saying at 11.1? They are saying in the diagram, cos DE, EF, and DF are drawn in the circle with center O. KFC is a tangent to the circle at F. So we have this cos DF, DE, and FE, right? No problem. They are saying KFC, this line KFC is a tangent to the circle at point F. Fine. So they want us to prove the theorem which states that angle F, which is the angle formed by DF and FK, is equal to angle E. So they want us to prove the theorem which states that angle F, which is the angle formed by DF and FE, is equal to angle E. So where's DF? DF and FE. So they want us to prove that this angle over here, is equal to that angle E over there. So this is the Tan-Chord theorem. Okay, so let's go over it. So this is our proof, right? So we need to construct some few things first. Construction. Fine. What do we do first? So we draw a diameter FO, let's say it's FOZ. Let's draw a diameter FOZ, a diameter. So where is this diameter coming from? Saying from F passing through O to Z. So with F, F is here. F passing through O to Z over here. So this is our diameter FOZ. No problem. What else do we do? We want to prove that this angle is equal to that angle over there. Right? So what do we do? Join this Z and E. You should join the two. So the second thing that we do, we're going to say is join ZE. Right? So join ZE. Done. So you know this angle, right? Is this one over here. Fine. Then what else? So we'll say, okay, this is maybe angle 1. Let's say this is angle 1 over here. And this is angle E, of course. Let's say this is on this angle 1 as well. And you know this angle is this one, which is DFK. It's angle F, this one. No problem. So look now. Here's what you can say. This is FZ is a diameter. And look at E1 and angle E. That's subtended by this diameter FZ. So E1 and angle E, they make 90 degrees, because those are angle in a semicircle, because you know diameters, they subtend 90-degree angles. So what we'll say here, we'll say, okay, angle E, which is this angle, plus that angle over there, which is E1, angle E1, this is 90 degrees. Why? This is the angle, this entire angle over here is this 2. This entire angle over here is subtended by what? By a diameter. So this is angle in semicircle. Right? No problem. Look at a similar thing. This angle here, which is your angle F and angle F1, they also make 90 degrees, because this is a tangent and this is a radius, FO. So you know that a tangent is perpendicular to the radius at the point of contact. So what you will say, okay, our angle F plus angle E1 plus angle F1, they also make 90 degrees. Why? These are because our tangent, what is our tangent? Our tangent, KFC, is perpendicular to our radius, which is FO. Right? Fine. So 9 is the same as 9, which is this side is equal to this side as well. Therefore, your E, angle E plus angle E1, they make up your angle F plus your angle F1. Right? So we're trying to prove that this angle over here is equal to this angle over here. So if you can prove that this one is the same as that one, they would cancel out, right? So let's go and have a look. Look at F1, sorry, E1. E1 is subtended by the arc dz. E1 is subtended by the arc dz. And look at F1, the same F1 is coming from the same dz. So these are angles that are subtended by the same arc. These are angles in the same segment, so they should be equal. So what we'll say, look, E1 is subtended by, is coming from dz, and so is F1. So these two angles are equal because these are angles that are subtended by the same arc. In that case, what we say is, okay, E1 is equal to F1. Why? Angles in same segment, which is the angle that are subtended by the same arc or same chord. In that case, now these two are equal. So your angle E, which is this, plus E1, which is that, is equal to your angle F, right, plus angle F1, which is the same as E1. Transpose this to the other side, so these two will cancel out, and you will be left with angle E equal to angle F. So we have proved this thing here. So we've proved this. And we're done with 11.2. So what I'm going to do, I'm going to clean the board. So we're done with 11.1. What I'm going to do now, I'm going to clean the board, and then we do 11.2. And I hope this does make sense to you, as it does to me. So let's clean the board, and we do 11.2. Okay, so now we're done cleaning the board, and we're going to do 11.2. So 11.2 read as follows. They're saying in the diagram, PK is the tangent to the circle at K. Chord LS is produced to P. N and M are points on KP and SP respectively, such that MN is parallel to SK. Chord KS and LN intersect at T. So let's have a look at the diagram. They're saying PK is the tangent to the circle at K. So here's P, here's K. So this line PK, right, the line PK over there, is the tangent to the circle at K. So let's highlight this tangent of ours. So PK, is it this line over here? It's a tangent. It's a tangent to the circle, right, at point K over there. Right? No problem. What else are they saying? They are saying now LS is produced to P. So we have a chord LS. So here's a chord LS, and it's extended to P, which is the end point of this chord PK. Fine. They wanted to say M and N are points on KP and SP respectively, such that MN is parallel to SK. So you can say M is on what? M is on SP, right? So M is on SP over here. Here's M. And N is on PK, such that this MN is parallel to SK over there. They went on to say that chord KS and LN intersected T. So the chord KS, which is this chord, and the chord LN, they intersected point T over there. Fine. Let's go to the first question, which is 11.2.1. 11.2.1. What are they saying? At 11.2.1, they're saying prove, giving reasons, that angle K4 is equal to angle M, which is the angle formed by NM and ML. So 11.2.1a, they're saying show that angle K4 is equal to angle M, which is formed by NM and ML. So they want us to show that K4 is equal to angle M. This angle M of yours is formed by NM and ML. Where's NM? NM is this line over here. Where's ML? ML is that line over here. Which is, they're saying this angle over here, right? So essentially what they're saying, they want us to prove that this angle over here is equal to that angle over there. That's what they want us to prove. No problem. So how are we going to go about this? If you look at K4, it's the angle between the tangent and the chord, right? K4 over here is the angle between the tangent and the chord. So, if you watch my back action sessions, which is why I was teaching Euclidean geometry on my playlists, you'll find that I did explain the Tan-Chord theorem. I said that the angle between the tangent and the chord is equal to the angle that the chord subtends on the other segment. So, K4 is an angle between this tangent KP and the chord KL. So the angle between the tangent, right, which is the angle between the tangent and the chord, which is K4, would be equal to the angle that this chord subtends on the other side, right? So we have a tangent, we have a chord. So the angle formed by the tangent and the chord would be equal to the angle that this chord will subtend on the other side. So which means this angle K4 of yours is equal to this one over here, right? Which is the angle K4 is equal to what? Is equal to angle S1. Why? Because of the Tan-Chord theorem. What is my tangent? My tangent is PK, right? And my chord is what? Is KL. So the angle between the tangent and the chord is equal to the angle that the chord itself subtends on the other segment, which is the angle formed by chord PK and the angle formed by the tangent PK and chord KL will be equal to the angle that KL subtends on the other segment. Fine. Now, we have shown that this is equal to this. Now, let's connect this to that. If you look at these two, these are corresponding angles on parallel lines. Because look at this, we have a line PL here, right? And this line PL is intersected by two parallel lines. So your PL is a transversal intersected by the two parallel lines. So the two parallel lines will intersect your transversal, which is your PL in this case, in the exact same way. So which means the corresponding angles on parallel lines will be equal, which means your angle S1 will be equal to M1 and M2, right? So in this case, this is what we want to prove, of course. It's okay, my angle S1 here, which is this angle here, is equal to this angle here, which is M1, M2 plus M3, angle M1 plus angle M2 plus angle M3. But if you look at angle M1 plus angle M2, it is NML, which is this angle M, which is this angle we want to prove here. So which is the same as angle M. What is the reason for this? For this, what we say? These two are corresponding angles. So our result will be like corresponding angles on parallel lines. Why? Because MN is parallel to what? To SK. So look now, your K4 is equal to angle S1. Your S1 is equal to angle M. Therefore, these two are equal, which is what we wanted to prove in the first place. So therefore, angle K4 is equal to this angle of yours here, which is your angle NML. Done here. So we move to B. What are they saying at B? At B, they're saying, prove giving reasons that KLMN is a cyclic quadrilateral. So they wanted to prove that KLMN is a cyclic quadrilateral. So you might be wondering, what is a cyclic quadrilateral? Also, you can check my playlist on my bed action. I did cyclic quadrilaterals there. Right? I explained them. So, what is a quadrilateral to begin with? A quadrilateral is just a four-sided shape, a four-sided flat shape. That's how I would define it. Now, if you are speaking of a cyclic quadrilateral, which means, of course, it's a quadrilateral which is a four-sided flat shape, right? But now, for it to be cyclic, there should be a circle of a perfect radius, such that that circle will connect all of its vertices, which it will pass through all of its corners. So in this case, we were saying KLMN is a cyclic quadrilateral, which means there is a circle that connects all of these points. Right? We're saying there's a point, there's a circle that will connect all of these points. Maybe a circle like similar to this. Right? So there is a circle similar to this. That's what we're saying if you're saying there's a quadrilateral. If you're saying your quadrilateral is cyclic, which is they exist a circle of a nice radius, a perfect circle, such that it connects all the vertices of your four-sided shape, which is your quadrilateral. Then that will make your quadrilateral cyclic. Now, the question becomes, how do you prove that your quadrilateral is cyclic? So, if you watch my bed action sessions on my playlist, 1, you must show that the opposite angles of a cyclic quadrilateral are cyclic. Number 2, you must show that an exterior angle of your quadrilateral is equal to the interior opposite angle, right? Number 3, you must show that there's a line segment or 2 points that subtend equal angles on the same side. Those are the 3 conditions. Let me repeat them again. To show that a quadrilateral is cyclic, there are 3 conditions that you need that are enough to show that, right? You don't need to show all of them. Showing one will do the work. Show that the opposite angles of your quadrilateral are cyclic. 2, you must show that the exterior angle of your quadrilateral is equal to the interior opposite angle, right? Number 3, you must show that 2 points or you must show that 2 points or maybe there's a line segment on your quadrilateral that subtends 2 equal angles on the same side. But let's look at this. So we're looking at triangle at a quadrilateral KLMN. So we want to show that KLMN is cyclic, right? Fine. Look, if you look at K4, K4 is between PK, is formed by PK, right? And this chord, KL. But you can also look at this length here as an extension of one side, right? So if you're looking at KLMN, so this is an exterior angle of this quadrilateral, right? If you're looking at this quadrilateral here, K4 is an exterior angle of this quadrilateral. And we have shown that this exterior angle of ours is equal to this angle here. So that is enough to say that KLMN is a cyclic quadrilateral because the exterior angle is equal to the interior opposite angle. It's one of the conditions. If you are unclear, go to my playlist and watch my bed actions. You should be fine if you watch all those videos then. So what I will say for now, I'll say, okay, angle K4 is equal to, which is this angle here, is equal to this angle over here, which is angle M, right? Or maybe you can say M2 plus M3. Why? Because we proved this in where? In 11.2.1a. Therefore, we'll say now KLMN is a cyclic quadrilateral. Why? Because the exterior angle of this quadrilateral is equal to the interior opposite angle of the quadrilateral. Therefore, it is cyclic. Because one of the conditions, because I said, in order to show that a quadrilateral is cyclic, you must show one of the 3 conditions. One, the opposite interior angles are supplementary. 1. Number 2, that you can show that an exterior angle of your quadrilateral is equal to the interior opposite angle. Number 3, you must show that there is a line segment or 2 points that subtend equal angles on the same side. So the second one is the one that we've applied here, and we're done with this. Now, let's move to the third one. Another question, which is 11.2.2. So, what are they saying? 11.2.2. They are saying, prove giving reasons that triangle LKN is similar to triangle KSM. So, they want us to prove that triangle LKN, right, is similar to triangle KSL. So they want us to prove this. So the first thing that I will do, let's go and identify these triangles. Triangle LKN, where is triangle LKN? Triangle LKN is this triangle LKN. So it's this triangle over here. I'll say it's this triangle over here. LK and N. So it's this triangle over here. It's this red triangle. So I don't need to use it. LKN. So that's saying we must show that this triangle is similar to what? To triangle to KSM. Where is KSM? KSM. So let's try to make it green maybe. K S KSM. So this part also goes with this triangle. Okay, so they want us to prove that triangle LKN, this triangle over the red triangle, is similar to triangle KSM, which is the green triangle over here. Fine. How do we show? Actually, what does it mean for two triangles to be similar? As of today, I haven't done sessions on these, so I'll try to explain it to my very best, but I'll do the predictions for that part as well, right? Where I'm going to teach the similarity of this. So let's go. So when you're saying two triangles are similar, you are basically saying they are scale division of each other. The scale factor can be 1. If the scale factor is 1, which is those two triangles are identical, which is they're identical, which is they're congruent. But the scale factor might not be 1, which means one triangle is a bigger version of the other, or one is a smaller version of the other. So when you're looking at this triangle, they look exactly the same. One looks bigger or one looks smaller, or they're exactly identical. So if two triangles are similar, the corresponding angles are exactly the same, right? The corresponding angles are exactly the same. And the ratio of the corresponding sides is also the same. So if you want to show that two triangles are similar, you can show that the ratio of the corresponding sides is exactly the same, or the corresponding angles are the same, right? That's what you do. So when you're showing that the corresponding angles are the same, you do not need to show all three corresponding angles that they're the same. Showing two will be enough, because we can find the third one by separating the two that we have shown, or the sum of the two that we have shown. So in this case, if we want to show that this triangle is similar to this one, what that means is that angle L of this first triangle is equal to angle K of the second triangle. Angle K of the second triangle is equal to angle S of the second triangle, and angle N of the first triangle is equal to M of the second triangle. So the order in which these letters are written also matters, because if you're talking about, if you're saying these two triangles similar, essentially you're saying this angle is equal to this one on the second one, this one is equal to this, and this is equal to that. And if you say LK over KS, it should be the same as KN over SM, which is the same as LN over KM. That's what that means. So in this case, we need to show these things. So showing two will do the work. So in this case, let's try proving this similar using angles. So let's look at angle L of the first triangle. LKN. Angle L, so this is L1 and this is L2, right? Let me just double check. Yes. So angle L of the first triangle is L1. So which means you must show that L1 is equal to what? L1 of this triangle equal to angle K of the second triangle. If you look at angle K of the second triangle is green triangle, which is angle L1 should be equal to angle K2 over here, right? So we must show these are equal. Or the other angles that you can look at, angle K of the first triangle. Where is K of the first triangle? K of the first triangle is all of this, because if you LKN, so it's this triangle, right? So if you're looking at this triangle, angle K is all of this angle here, which is K1 plus K2 plus K3. So you can also show that maybe your K1 plus K2 plus K3 is equal to what? Is equal to, which is angle K of the first triangle, is equal to angle S of the second triangle. So second triangle is what? Is KSM. KSM, which is equal to S2, right? So show equal to S2. So if you can show that these two, if you can be able to show that only these two, you are done. It will be enough. Just showing two pairs of corresponding angles, it will be enough, I'm not sure if that was correct, but if you wanted to show that these two are equal and these two are equal, that will be enough. Now, the third one that you might not need to show if you have shown this is shown that angle N of the first triangle. Where is the first triangle? It's the red triangle LKN, which is your N3. This is the 3 here, right? This is 1, 2, 3. So this should be 3. N3, angle N3, is called angle M of the third triangle. Third triangle, M is M3. Here is M3 because it's KSM. So it's M3. If you can show these as well. So if you want to show that these two triangles are similar, you can either show these two, or show these two, or show these two. Any two would be enough. You can show that these two are equal, or these two are equal, or these two are equal. That will be fine. You will have shown that these two triangles are similar. So let's try to do that. Look, the most easier ones to me. Look at N3 and M3. Look, here's N3. N3 is subtended by KL. N3 is on the circumference of the red circle. Right? If you look at M3, is subtended at the circumference of this red circle here. Right? It's subtended by KL. Look at KL also subtends N3. So look at M3 and N3. They are both subtended by the same chord. So those are angles in the same segment because they are both subtended in the same segment by the same chord KL. So this angle and that angle are equal. Those are the easiest to me. So I was okay. Angle N3 is called angle M3. But they are both on the red circle, right? These are angles in the same segment, which is they are both subtended by the same chord in simple terms. Right? No problem. So we've shown this one over here. So if we can just show this one or this one, we're done here. If you can just show this angle, these two angles are equal, or show these two angles are equal, we're done. So how can we go about this? K1, K2, and K3 equal to S2. K1, K2, and K3, which is this angle over here, we're saying it's called A2, S2, which is this angle over here. You see that these angles are almost all in a line, right? They're almost all in this line over here. They're almost all in this line because K1, K2, K3, they're almost all in this line. And if you look at these, they're also almost all in this line as well because you see S2, you're just missing that. Even here, you're just missing that. Right? So what we can say, we know that K4 and S1 are equal because we proved them somewhere. Look, this and this are equal because of the Tan-Chord. So if we add this and that, it will give us 180 degrees. And if we add these two, are going to give us 180 degrees. Right? So let's do that. We can say, okay, K1 plus K2 plus K3 plus K4. These angles, they all give us 180 degrees. Angles on a straight line. Right? Fine. What else? We're going to say S2 or S1 plus S2 called 180 degrees. These are also angles on a straight line as well. So 180 is called 180 degrees. So the right hand side is called to the right hand side of this one, which means these two are also equal, which means your K1 plus K2 plus K3 plus K4. These are angles, of course. They are equal to S1 plus S2. These are angles. Right? Fine. But remember, we said that K4 is equal to S1 because of the Tan-Chord, right? Which is this angle and that angle are equal. So they can cancel out. So we said that K4, angle K4 is equal to angle S1 because of the Tan-Chord, right? Which is this one here. So if we're saying this is equal to that, we can just put K4 and put K4 there. Then they will cancel out. So what we'll say is, look, K1 plus K2 plus K3 plus K4 is equal to S1, right? It's equal to, wait, called S1, which is S1, which is also K4. So we can say it's called K4 plus S2. So this and that will go away, right? And we're left with K1 plus angle K2 plus angle K3. These are angles. Is equal to angle S2. So we've shown that this angle here is equal to that angle over there. So this is enough. We can stop here. We can say, therefore, triangle LKN is similar to triangle KSM. By what? By angles. The corresponding angles are equal. So showing just two is enough. You don't have to go far. But if you want to go far, you can, but you don't have to. So I don't have space anyway for the next question. So what I will do, I can just be extra and maybe try to do that one as well. But this, we're done with this question. Let's say maybe you wanted to show L1 and KL1 and K2, which means you wanted to show that this angle L1 is equal to angle K2 over here. Right? No problem. So how can we go about this? Want to show that L1, which is this angle, called K2, which is this angle over here. Right? That's what we want to show. How can we go about this? Maybe you can say, look, you can say L1 and M2. Look, they are both subtended by the same, on the right circle, you have the chord Kn there. So you can see your L1 is subtended by Kn, and so is M2. So this angle and that angle, they're both subtended by the same chord. So these two angles are equal because these are angles in the same segment, right? And this one here is also equal to that because look, these are alternate angles on parallel lines. So we can say, look, you can say L1, that angle over there, is equal to the angle M2 over there. Why? The reason we're saying this, we're saying these are angles in same segment, which is these are angles that are subtended by the same chord. Right? And then, and say now, look at this. This M2 is equal to, look, M2 is equal to K2, because these are alternate angles on parallel lines. This line is parallel to this one. So we can say your, what is it? Your M2, which is this angle here, is equal to your K2. Why? These are alternate angles on parallel lines because your MN is parallel to SK. Right? So your L1 is equal to M2, your M2 is equal to K, your L1 is equal to M2, and the same M2 is equal to K2. Therefore, your L1 is equal to your K2, which is the third condition over here. I said you don't need to show all three of them. You can show these two, or show these two, or show these two, and it will be enough. So what I'll do now, I'll clean the board, and then we'll move to the next question, which is 11.2.3. So let's clean the board and do 11.2.3. Okay, so now we're done cleaning the board, and I've written all the stuff that we've done so far from 11.2.1 to 11.2.2. Now we're going to do 11.2.3. What are they saying? They're saying if LK is equal to 12 units and 3KN is equal to 4 SM, determine the length of KS. Right? So what is happening? They are telling us that LK is equal to 12 units. Where is LK? LK is equal to 12 units, which is that length over there on the red triangle is equal to 12 units. Right? So the length on the red triangle is equal to 12 units. Fine. They went on to say that 3kn is equal to 4sm. So they're saying 3kn. They're saying 3kn is equal to 4sm. Right? No problem. What do they want from us? They want us to find the value of ks. They want us to find the value of ks. Who is ks? Ks is this length over here. So they want us to find this length over here, this green length over here. This one they want us to find. They want us to find this length over here. Fine. So let's first deal with this. What does this tell us? So what we need to do here, let's divide by 3 this side and 3 that side, right? So that we remove this number completely this side. And this side, let's divide out. Okay, so what we're going to be left with is going to be what we're going to be left with is kn is equal to 4 over 3 sm, right? So let's divide by sm this side and divide by sm this side. So you're left with is kn over sm is equal to 4 over 3. Right? No problem. So if you see a ratio like this is kn over sm. So is kn over sm is equal to 4 over 3. This is a ratio, and so is that one. So the question becomes, does that mean kn is equal to 4 and sm is equal to 3? That's not true in general. Not in general. It can be, but not always true. That's what I mean when I say not in general. So the nicer way of thinking of it, I always think of it as maybe some sort of maybe 4a over 3a, where your a is a positive real number. So you can think of this as the simplest form of whatever the lengths of kn and sm were. So this is the simplest possible ratio of the length of kn to that of sm. That's how I think of it. Fine. So if I have a situation like this, I can say, okay, the length of kn was 4a. Where is kn? Kn is this length over here. So the length was 4a. So I'll put 4a here. Right? And the length of sm was 3a. Where is sm? Sm is this length over here. So it's okay. This is 3a. Okay, not a problem. So we have this ratio, right? And we said this ratio is equal to what? We said, what we're trying to find this ratio over here. Okay. So what are we going to say? We said, okay, we have kn over sm, right, to be equal to 4 over 3. No problem. Where is kn? If you look at kn, kn is on the red triangle, and sm is on the green triangle over here. So on the previous question, we proved this. We proved that triangle triangle LKN, which is the red triangle. So in the previous question, we proved that the red triangle LKN, right? LKN is similar to what? Is similar to the green triangle, which is what? Which is KSM. That's what we did on the previous question, which is triangle KSM. We proved that these two triangles are similar. So, and I said that if two triangles are similar, the corresponding angles are equal in measure. That's what we use to prove this. And I also said that if two triangles are similar, the ratio of the corresponding sides should be equal. So if you say LK, this LK, and divided by KS, it should be the same as that of KN over SM, which is the same as LN over KM. As long as you take the ratio of the corresponding sides, those ratios will always be equal if the two triangles are similar. So we've already proved that these two are similar. So if you take the ratio of the corresponding sides, we know that those ratios will be equal. For example, here you are given that Kn over Sn. Where is Kn? Kn is these two. If you look at Sn, Sn is also the last two. So which means, look, in that case, Kn, which is this Kn over Sn, right? It should be the same as what? It should be the same as Lk maybe, over the Ks there, which is equal to what? Which is equal to Ln over Kn over here. Why? We're applying this. This will work because these two triangles are similar, because these are corresponding ratios of similar triangles, because the triangle LKN is similar to triangle KSM, right? No problem. So, you know this ratio over here. You know this ratio because it's 4 over 3, right? And you're trying to find what? We're trying to find Ks, which is, this is what we're trying to find over here. But you will need Lk, but you're given Lk to be 12. So you have 4 over 3, and you have 12, you are looking for Lks, which is, I think, is easy. Because here, at this ratio, you just put your 4 over 3, which is what you're given, right? Which is this, is equal to Lk. Your Lk, you're given Lk is to be 12, and your Ks is what we're looking for. Then you cross multiply and solve to Ks, you get that your Ks is equal to what? Is equal to 12 over 4, right, times 3. That's what you have. Therefore, your Ks should be about 9. So it should be 9, because this over this is 3. 3 times 3 is 9. So your Ks is equal to 9 units. Where is Ks? Ks is this length over here, and it's equal to 9 units. We're done with this. So, we move to the next question, which is 11.2.4. So, let's go to 11.2.4. 11.2.4. So, what are they saying? They are saying 11.2.4. If it is further given that NL is equal to 16 units, LS is equal to 13 units, and KN is equal to 8 units, determine the length of LT, giving reasons, of course. So we're given that NL, who is NL? NL is the length of the right side here. So NL is this length over here. We're given that this length is equal to 16 units, this entire length. Here is 16 units. And we're given that LS is equal to 13 units. So is LS? This length over here. This length is equal to 13 units. From L to S, 13 units. What else? Kn is equal to 8 units. Kn. Where is Kn? Here is K. Here is N. It's equal to 8 units. So this length over here is equal to 8 units. Right? No problem. What do they want you to find? They want us to find the length of LT. They want us to find LT, which is this length over here. Right? No problem. So look, this length is parallel to this one. This length, KS, is parallel to NM you're given. So if you look at triangle LTS and triangle LNM, you can apply the proportionality theorem, because these two sides are parallel, which is this side over the entire length is equal to this side of the entire length. But you're looking for LT, which is this small part here. You have the entire length there, which is not a problem. You have this one here as well, here, but you don't have the entire length. You don't have this part. So it would be nice to have this part. So we'll first have to find MS over here. So how can we find MS? Look, we said this is 3A and that is 4A. And that 4A is equal to 8. So we can find the value of A. This value of A is the same as that one over there, because it's the same A that we're cancelling out. Right? So what you can say, okay, my 4A that I was given there, my 4A is equal to 8, which is my A is equal to what? Is equal to 2. In that case, that would mean your MS over here is equal to 3a, which is equal to 3 times 2, which is equal to 6. So which means we would have that this length over here, 3a, is equal to 6 units. Now look, you have triangle LTS and triangle LMN with these two being parallel. So this ratio of the entire side, and sorry, LT over LN is equal to LS over LM, because this is proportionality theorem, because these two sides are parallel. If you're not happy with finding MS this way, you can use the same similar way as this one. What are you looking for? We're looking for MS, right? Which is we're looking for this. We're looking for this over here. We have Kn, we're given Kn. Kn is equal to 8 units. There it is. Which is going to put Kn here. We're looking for Sm. Right? Lk. You have Lk, you're given Lk. Lk was given to be 12. Ks, you found Ks to be 9. So you only find this. So what I'm saying, you can say, use this as well. Say Kn, I'm doing the same thing, doing the same calculation. So I'm going to say, okay, look, Kn over Sm is equal to what? It's equal to Lk over Ks. Same ratios, same thing. Why? I'll say it because these are corresponding ratios of similar triangles, right? So you'll say, or maybe you can just say triangle LKN is similar to triangle KSM. And then LK, KN, what is it? KN, you are given KN to be 8. There it was. So put 8 is equal to what? Or 8 over SM, which is what you're looking for, is equal to LK. What is your LK? Your LK is, you are given LK to be 12. There it was. So it's 12 over KS, which is what we found to be 9. So if you solve the SM, you find that your SM is equal to what? Your SM is equal to 8 times 9 over 12, right? So your SM is equal to, if you look at this, this is 12, right? And the 12 is 3 times 4. So this 4 will get here and we'll have with 2, and this will get here and you'll be left with 3. So this is 6, 3 times is 6. So this SM is the same as that one over there. So what do we do from here? So 1 LT. In that case, we say, okay, in two triangles, triangle LTS, in triangle LTS, and triangle LNM, we can say that if we say LT over the entire side should be the same as LS over the entire side. So if we say LT, right, over LT with LT against LT over LN should be the same as LS over, it should be the same as LS over LN. We're applying the proportionality theorem here because it works because SK is parallel to MM. So MN is parallel to SK, right? So what is your LT? Your LT is what you're trying to find over LN. What is your LN? LN is 16, which is equal to LS, which is 12 over, what is LS? LS is 13, sorry. It's not 12, it's 13. So LS is 13 units. 13 here. So 13 times 16. So the answer is 208 over 19, which is equal to 10.95 units. So we find that if we want LT over here, this small length over here is 10.95 units. And I'm done here. And I hope this question does make sense to you, as it does to me. Thank you for watching. Now let's move to the next question paper. Cheers.